Hello, Patricia.
Yes, Mr. Zassi, give me just a second to get out of the other room.
Okay.
Hi, Mr. Zassi.
Hi. Okay, guys, I'm going to share my screen with you so I can have animation on the PowerPoint. Can you guys hear me?
Yes, sir.
Okay, so let's begin, okay? Students, today topic is going to be basic concepts of probabilities, permutations, and combination. These topics are they're real broad. So what I did, I just got what I think is the most important of these topics, and also like the foundation. Okay, because if I go to the harder material without the foundation, it'll be hard for you guys to understand it. Okay, so hopefully you guys can, will enjoy this PowerPoint or this presentation. Okay, so let's start first of all with introductions to probabilities. Okay, here we go. This is from section 8.2. Here are some some definitions or like concepts that you have to know the meaning of. For example, random experiment, a process by which we observe something uncertain. After the experiment, the results of the random experiment is known. Okay, now sample space. The sample space is denoted by capital S, the set of all possible outcomes of a random experiment. For example, here are examples of the sample space. If we flip a coin, say once, can it be just heads and tails? So that's my sample space, heads and tails, which is going to be denoted by capital S equals to the set of H and T for heads and tails. If we roll a fair die, what does it mean by a fair die? It means that the dice or die is not loaded, because at times there's people that are not honest and they load the dice so that way they can go into their favor. So a fair die is a die that has equal amount of weight on all the sides. Okay. So a sample space, it can be a 1, a 2, a 3, a 4, a 5, or a 6. So that's my sample space. Okay, now at times it's wise to do like a little tree diagram so you can see the sample space, like because many students they like to observe things so they can understand it. So here I'm going to show you an example of how to draw a tree diagram. So to find the sample space of an experiment, at times it's easier to draw a tree diagram. So find the sample space of flipping a coin twice. Okay, here's my flipping a coin twice. So here's my first flip. It can be a heads, right? Or it can be a tails. After we do the first flip, here comes a second. So if it's going to be heads first, then from the heads, it can be again heads, or it can be tails. And also, if my first flip is tails, after the second flip, it can be heads again and tails. So what's my sample space? It can be heads, heads. It can be heads, tails. Or it can be tails, heads. And tails, tails. So my sample space is S equals to HH stands for heads, heads. HT stands for heads, tails, and TH stands for tails, heads, and TT stands for tails, tails. Okay, now an event. An event is an outcome or a set of outcomes of a random experiment. An event is a subset of a sample space. Remember last week, guys, about the sample space and the subsets? Okay, now, for example, if the sample space of flipping a coin is the set is heads, tails, then one event can be heads, right? That means one event can be heads because this set is a subset of the sample space, who represents the outcome of heads. Okay, now checkpoint. Okay, just make sure that you guys are understanding the concept here. Suppose a die is tossed. A die stands for just a single dice. Single die. And then when it's dice, it's plural. It means two or more dice, two or more die that are tossed or flipped. Write the given events in a set notation. So first, guys, we have to remember what's my sample space. My sample space is equal to 1, 2, 3, 4, 5, 6. Because when you toss a die, it can be a 1, or it can be a 2, or it can be a 3, or a 4, or a 5, or a 6. That's my sample space. So for part A, the number showing is less than 3. So it can be a 1, right? It can be a 2. Can it be 3? Because if it says the number is showing is less than 3, it cannot be 3 because it's saying less than 3. So this is the event of tossing a die that's less than 3. How about B? The number is showing a 5. That's the event. For C, the number is showing an 8. There's no 8, so it's the empty set. Now D, the number showing is even. Right, so even, it can be a 2, it can be a 4, or it can be a 6. That's the event for the number to showing that it's even. If you guys are okay, just put yes on the chat, please, so I can move on, because this is crucial. Okay, I'm going to move on then, okay? Now, basic probability principles. We let S be the sample space of equally likely outcomes, and let the event E be a subset of S. Then the probability that the event occurs is the probability of the event is equal to the number of the event times the number of the sample space. Okay, by this definition, the probability of an event is a number that indicates the relative likelihood of the event. And again, I put here in red because this is crucial here, it's important. The N stands for the number of the event. N of E is the number of elements in the event. And N of S is the number of elements in the sample space. Okay? So checkpoint. Suppose a single third die is rolled with a sample space S equal to the set of 1, 2, 3, 4, 5, 6. Give the probability of each of the following events. So for A, they're going to call it event E. For B, they're going to call it event F. And for C, they're going to call it event G. So for A, it's event E. It's saying the die shows an even number. Okay? So the probability of E, right? For it to show even number is going to be 2, 4, and 6, right? So it's 3 elements. And N of E is 3, and N of S is 6. So then the probability of event E is equal to the number of the elements in E over the number of the elements in S, which is 3 over 6, which is equals to 1/2. This here, guys, should have been like a lowercase n. Okay, so that was my bad right there. Now for B, the die shows a number less than 10. Hey guys, so less than 10 from the sample space, won't it be all of them? So it's 6 elements. So the event, the number of E is 6, and the sample space is 6. So the probability of event F is equal to 6 over 6, which is equal to 1. Now the die shows an 8, right? It's for the event, for the probability of G. There's none because there's no 8 here. It's only 1 through 6. So it's going to be 0. So the elements of n is 0, and the sample space is 6. So it's going to be 0 over 6, which is 0. There's no chance that it can be an 8. Okay, now checkpoint. A single playing card is drawn at random from an ordinary 52 card deck. Find the probability of drawing a queen for part A, a diamond for part B, a red card for part C, and D, a face card or an ace card. Okay, now when I do this, when I do this topic in class, guys, I actually bring a deck of cards, and I bring some dice, so students can actually see. Here in this PowerPoint, I got a little bit creative So I brought the cards to you guys, and also I mean, what's a face card and all that stuff. So all this, I'm going to give you like a picture of what it means or what it represents. Okay, here's a set of deck of cards. Okay, a deck of cards has 52 cards total. Okay, these are called clubs, which there's 13 clubs because the ace is like a 1 or a 15. So here it's going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So there's 10, and these are called face cards, the queen, jack, and king. So there's 13 cards for each suit of clubs, of spades, of hearts, and diamonds. So again, there's 13 spades. Same thing, there's 13 hearts, and there's 13 diamonds. So the total will be 52. Okay, now, there's 26 black cards, right? Because 13 and 13, these are black, so there's 26. There's also 26 red cards. And there's also 3 face cards of each suit. You guys might be thinking, so, I mean, what are the face cards? The face cards are the jack, the queen, and the king. But for each suit, for example, there's 3 spades, there's 3 clubs, there's 3 hearts, a face card, and there's 3 diamonds, a jack, queen, and king of each suit. Okay, now, so with that said and done, let's do part A. So for the solution, guys, we're going to use this formula here. The probability of the event is equal to the number of the event, the number of elements in the event times the number of elements on the sample space. And we notice the sample space will always be 52, right? Because there's 52 cards. So now let's do part A. Probability of a queen. So we know that there's, so n of queens, there's 4 queens because there's 1 from each suit. There's the clubs, the spades, the hearts, and the diamonds. So that's why it's 4. And my sample space is 52. So all we do is reduce it and simplify a fraction term. So it will be 4 over 52. If we reduce this to 1 over 13. So this is my answer, 1 over 13. Okay, now for a diamond. For a diamond, we notice, guys, there's 13 of each suit, so there has to be 13 diamonds. So n of diamonds is equal to 13 over the sample space, which is the same as before, is 52. So 13 over 52 will give us 1/4 in reduced form. Now, the probability of a red card, right? So the red cards are both the hearts and the diamonds. Remember, guys, there was 26 red cards, so it's going to be 26 over 52. If we reduce it, it's going to give us 1/2. Now, for a face card or an ace. So here, guys, it's a face card or an ace. So remember, guys, there was 13 face cards, right? 13. I mean, not 13, there's 12. There's 3 from each suit, so 3 times 4 is 12. And aces, there's 4 aces, 1 on each suit. So it's going to be number of face cards, and aces is going to be 12 plus 4, right? These are my face cards, and this is the aces. Over 52. So that becomes 16 over 52, and then we round off. I mean, not round off, simplify. So the answer is 4 over 13. Okay, I'm going to move on, okay? Now comes, this is 8.3. What I just showed you was a basic foundation for an 8.2. Now comes 8.3. These are basic concepts of probabilities. So this is called the addition rule for probabilities, which is for any event E and F from a sample space S is a probability of the union of E and F equals to the probability of E plus the probability of F minus the probability of E intersects F. And remember from before, guys, this is like an OR, and this is like an AND. The OR is like a union, and the AND is like intersection. So this is example 1 from the book. I thought this was a very good example because there's also some homework problems related to this roulette table. To the roulette turntable. So example 1. When playing American roulette, the croupier, who is the attendant, spins a marble that lands in one of the 38 slots in a revolving turntable. The slots are numbered 1 through 36 with 2 additional slots labeled 0 and 00 that are painted green. You see 00 and the green is here, and the 0, they're both green. half, this should have been up, guys. Half of the remaining slots are colored red and half are black. In roulette, the slots labeled 0 or 00 are not considered as even or odd. So find the probability that the marble will land on a red or even. Okay? So here we're going to let solution. We're going to let the set of red equal BR. So everyone that's here, guys, that's red, I put him here. And it's 1, 3, 5, 7, 9, and so forth. I got him from the turntable here. Okay. Now we're gonna let, right, it was red and even. So now the set of even be E. So E equals to 2, 4, 6. All these are the even numbers. And as you notice, the ones that were red, right, they were here, the 12, 14, 16, 18, they were red. And so were the 30, 32, 34, and 36, they were red. Okay, so these are all the even numbers. The rest of the even numbers, the rest of the black ones are going to be the ones in between. Okay? Okay, now. So here we go. So the probability of red or even equals to the probability of red plus the probability of even minus the probability of R intersects the even. So here we go. So there's total of 38, correct? There's 36 slots plus 0 and 0, 0 makes it 38. There's 18 red and 18 black, 18 even and 18 odd. And red and even, right? So these are this is what it means here, guys, by red and even. There's 8 because we have 1, 2, 3, 4, 5, 6, 7, 8. So there's 8 that are red and even. Okay? So now, you guys remember, here we find the probability that the marble will land on an even or a red or even, which means union, which means this is a symbol for or. So again, we're going to use the probability of the event. So here we go. So the probability of red, right, is 18 over 38, right, because there's 18 red. All these are going to be 18, and there's 38 total. Plus, how many are even? Another 18, right, because it's half and half. And remember that the 0 and 0, 0, the ones that are green, they're not even or red. They're not even or odd. Minus, where does a red intersect the even, which I got it right here, right? There was 8, which is 1, 2, 3, 4, 5, 6, 7, 8. So then, right, so we do the operations. It's going to be 28 over 38 because 18 minus 8 is 10. 10 plus 18 is 28. So 28 over 38 is my answer, right? And then we reduce it to 14 over 19. So that's my answer, guys. So again, every time that you see like a word problem, something like this, it's always wise to draw yourself like a picture. And when I teach this like in class, it's hard to draw the whole turntable, right? So that's why my students have access to my notes. That way they can see the notes as I put all this information on the board. But now I'm thinking to even uploading this PowerPoint to my lessons because these are, in my opinion, they're very, very good and they're very like observatory. Okay, so I'm going to move on then, okay? Okay, now example 2. Suppose two for dice are rolled. Find each of the given probabilities. For A part, the first die shows a 2, or the sum of the result is 6 or 7. So remember, guys, this is a keyword here, or. Or means, right, intersection. So for part A, again, we're looking for the A or B, right? This is what they're looking for the union. And the and means intersection. So this means or here. You see that word or means union. So this is a formula that they want us to use. So let A represent the first die, right? Because this will be set set A, and the two will be, this will be set A, and this will be set B. They B represent the event that the sum is 6 or 7. So again, set A represents that the first die shows a 2, and set B shows that the sum is 6 or 7. So for that, here's a copy, guys, of all the possible outcomes when you roll some dice. You see, guys, it can be, this is the first die, it can be a 1 and a 1, a 1 and a 2, and so forth. So it's going to be 36 total, right? Because there's 6 this way and 6 down, so there's 36 because 6 times 6 is 36. So that's going to be my sample space. Okay, now, if you notice, right, event A says they represent the first die shows a 2, you see? So this is event A. This is my first die, shows a 2, and so forth, right? So it's going to be 6, right? N of A equals 6 because there's 6 of them. 1, 2, 3, 4, 5, 6. And then for event B, it's going to be 11, that the sum is 6 or 7. Hey guys, when you do these type of problems, these across, for example, these are equal to 2 across. These are equal to 3 diagonally. These are 4 and 5. And these are 6 and 7, right? And then 8. I know my mouse is a little bit crooked, but that's 8. They're all equal to 8, 9, 10, 11, and 12. So for the sum to be 6 or 7, it's going to be 1, 2, 3, 4, 5, 6, 7, 9, 10, 11. That's why N of B is equal to 11. So let's plug it into the formula here. It'll be 6 over 36, right? That's for event A, 6 over 36, plus 11 over 36. Now, where do they intersect? Intersection, right? Here's my intersection, right? My intersection of A and B is the 2 and the 4, right? Because it belongs to both sets, and the 2 and the 5. So there's going to be 2. So that means there's going to be minus 2 over 36. Now, 6 minus 2 is 4. 4 plus 11 is 15. And then we have to simplify. You always simplify your fractions to lowest terms. So my answer is 5 over 12. And this is actually an example from the book. And also the one before that on the turntable. Okay, now for part B, the sum is 11, or the second die shows a 5. So solution for part B. Okay, so let's see here. So the sample space is again 36. So we're going to let A, right? We're going to let A represent the event. The sum is 11 because that's the first one. And let B, right? So these are ones that are 11 here. These two get up to 11, which is equal to 2, right? Because there's only these 2 here. Now then we let B represent the event that the second die shows a 5. This is my first die, this is my second die, so the one that shows a 5 on the second die will be this one here. You see those right there? You see all of them, the second die shows a 5. So there's going to be 1, 2, 3, 4, 5, 6. Now, where do they intersect? Wouldn't it just be right there? That's where they intersect. So it's only going to be 1. So once you have all this information, we plug it into the formula. 2 over 36 plus 6 over 36 minus 1 over 36. And that's my result, 7 over 36. And 7 over 36 cannot be simplified any further. So that's my answer. Okay, now here, we're going to show, this is called the complement rule. For any event E, the probability of the complement of the event is equal to 1 minus the probability of the event, or the probability of the event is equal to 1 minus the complement of the probability of the event. Now comes odds in favor. This is what most gamblers use, like in Vegas, the odds in favors to win or odds in favors to lose, stuff like that. So the odds in favor of an event are defined as a ratio of P of probability of the event to the probability of the complement of the event. Or it's going to be the probability of the event over the probability of the complement of the event. And the probability of the complement of the event cannot be 0 because it will be undefined. So here's an observation real quick to make your work easier. Okay, so I'm going to put this here, guys, right? Isn't the probability of the event equal to the number of elements in the event over the sample space? And same thing, the number of elements and not in the event over the sample space. So for example, if you're dividing, this is called a complex fraction because it's a fraction on top of a fraction. if you divide a fraction over a fraction, doesn't this become multiplication, right? You put the first fraction first, then the division sign becomes a multiplication, and the second fraction, you flip it, right? This one goes to the numerator, and that goes to the denominator. What happens with the sample spaces? Right? That becomes 1, or they cancel, right? So what's left? What's left is the number of the event over the number of not the event. This will make your work much easier when you actually do some of the homework. Okay. Again, this goes straight to the if they ask you for the odds, this is your answer. Just the number of the event over the number not of the event. Let me show you an example so that this can make more sense. This is number 27 from page 434. For the 1324 book, it says a marble is drawn from a box containing 3 yellow, 4 white, and 4 blue marbles. Find the odds in favor in drawing the given marble. So solution, right? There's 3 yellow to make it here. So this can be we can observe it better. So it's 3 yellow, 4 white, and 8 blue. So for A part, odds in favor in drawing a yellow. Now let's use this right here, which means yellow and not yellow. So how many are yellow? Is 3, right? There's 3 yellow. And not yellow are the ones that are left over. So 4 plus 8, which equals to 3 over 12, and that can be reduced to 1/4. And but you have to write it, guys. This is the actual answer. They want it like this, like in odds favor. This is the same thing as a fraction, or you can put it 1 to 4 in words, but this is how they want the answer. This means 1 to 4. As in favor of drawing a blue, same thing. Blue over not blue. So how many are blue? 8. How many are not blue? 7. So what are the odds? 8 to 7. For C part, as in favor in drawing a white. How many are white? There's 4 white. Not white will be 11. And that one cannot be reduced, so it stays how it is. It'll be 4 to 11. So this is very simple, guys. If you go from the actual odds to the simpler version of the number of elements in the event over the number of elements not in the event. Okay, now this will be from exercises 47 to 54, page 435. Since data from the 2016 General Social Survey can allow us to estimate how many hours people who classified their work status as part-time or full-time actually worked in the last week. For the following table to find the probabilities of the events. Okay? So again, we're going to use the same formula as before, right? So this is the probability of the event. And what's my sample space? My sample space is the total, right, which is 5091, 1,591. That's my sample space for every problem here. Okay, now, for it to be a full-time worker, right? So here's how you read like these type of tables. So a full-time worker is here, right? These are full-time workers. That's my total. These are part-time workers. That's my total. These are the people that work from 0 to 19 hours. That's my total, and so forth, right? So this is how you read this table here. So the probability for it to be a full-time worker, okay, there's 1,271. So the probability of a full-time worker is going to be 1,271 over 5091. But here, guys, they actually want you to round it up to 4 places. So this is the answer that they're looking for, approximately 0.7989. Same thing with 48, right? 48, they want the part-time worker. Again, we use the very same thing as before. This is the main formula here. So there's 320, right? Because for the part-time worker, there's 320. There's my total. So that's my probability of the event. We put in the calculator, round it up to 4 places, so it'll be 0.2011. Now 49, 50 hours or more, right? So 50 hours or more, wouldn't it be 393? So again, we follow the same procedure. Calculator, and we round up to 4 places. It's going to be 0.2470. Now number 50. between 0 to 19 hours, right? 0 to 19 hours, so it's going to be 106. Again, follow the same procedure. So it'll be 106 over 1,591, which approximately gives me 0.0666. Are you guys okay up to this point? Can I move on?
We have a question from Giselle. She asks, what does the equal symbol represent?
Which one? That one there?
I think that's the one she's mentioning, yes.
That means approximate. Every time where it says approximate, you put it like in little wiggly lines. That means approximation, that is not exact. For example, on number 47, when you have, like a normal equal sign, this means it's the exact. When they want you to approximate, right, to 4 places or to round off, then you apply the wiggly lines. Did that answer your question?
Thank you.
Oh, you're welcome. You're welcome. Okay, now guys, on the next page, I'm only going to do 2 more. I'm going to do I think 51 and 54. Okay, these are a bit more challenging because there's keywords that's going to tell you what to do. Again, it's with the same formula as before, and the sample space is the same. But now, 51. Okay, check this out, guys. This is a keyword. Remember that "and" means intersection. Part-time worker and someone who worked 40 hours or more. So we're going to look at the part-time worker. So we're looking about these right here. Okay, right? Part-time worker. And works 40 hours or more. So 40 hours or more won't it be 49 and 21, right? Because these people that are part-time workers, all these right here, these work 40 hours or more, which is 49 plus 21. Right? That's a keyword right there, "and." Which means, right, 49 plus 21, because these two worked 40 hours or more. And you simplify it, and that's your result. Okay, now, number 54. I believe, guys, 53 and 54 are the hardest one of all. Why? Because they have the "or." The "or" means, remember, union, or you put them all down, but you don't repeat them. Remember from last week? Okay, let's try this one then. The word "or." So be real careful and read the problem carefully before you start doing some of the work. Okay, so the "and" stands for intersection, and the "or" stands for union. Remember? So this is what we're looking for, the union or the "or." So P of E is equal, check this out. Right? So again, we're looking for part-time workers. So it's going to be 320 plus 106 plus 129 minus 77 plus 87. Let me show you why. Okay? Let A represent the part-time workers. Right? So this is A, the part-time workers, which is 320. Let B be the represent 20 hours or less work. So how many work 20 hours or less, right? So it's going to be these two here. So these are the ones that no, this is going to be here, guys, right? The total 29 hours or less are these 129 plus 106. That's what this comes from. And then minus these two here because you don't count them again. Okay, so check this out. So this is 320, and the ones that work 29 hours or less are going to be these two here, the 106 and 129. And then minus, right, where do they intersect? They intersect right here. That's why it's going to be 320 plus parentheses 106 plus 129 minus 77 plus 87, which are these two here. And here's my answer, right? So this is my total answer. So then it's going to be 391 over 5091, and it's going to be approximately 0.2458. And again, this is the hardest one from these type of problems. Okay, I'm going to move on, okay? Okay, now comes 9.2. This is multiplication principle, permutations, and combinations. So this is the definition or the formula that they want you to use. Suppose n choices must be made with m1 ways to make choice 1, m2 ways to make choice 2, and so forth until n choices, m choices, which means that ways to make n choices, which means the number that you want. Okay? So then it's going to be m1 times m2 times m3 times m4 until you get to mn. different ways to make the entire sequence of choices. Okay, so this is number 24 from page 477. It's saying how many different heating cooling units are possible if a homeowner has 3 choices for the efficiency ratings of furnace, 3 options for the fan speed, and 6 options for the air condenser. So use the multiplication principle. Okay. So now, number of choices for efficiency ratings, right? So it's going to be these. It's going to be these right here times these right here. That's what I have here. Number of choices for efficiency ratings of furnace, number of choices for a fan speed, and number of choices for the air condensers. So how many number of choices for the efficiency ratings of the furnace? So we have 3, right? And the number of choices for fan speed, there's 3. And the options, 6 options for the air condensers. So there's 6. So we're going to multiply them all out. And that's how you can get them. Because at times, for these, they actually want you to draw a tree also. Maybe if we have time, I'll show you how to draw a tree with something like this. Okay, because with a tree, you count the total at the end, and you count them, and it's going to be 54. Okay, but at times a tree is not that good of an idea, because if you have like 54, it's going to be hard to count them at the end, or else you have to draw like a real nice tree that you can actually read it. Okay, so there's 54 different units are possible. Okay, now this is number 28 from page 477. It says that the United Postal Service currently uses 5-digit zip codes in most areas. How many zip codes are possible if there are not restrictions? There should have been no restrictions on the digits used. How many will be possible if the first number could not be a 0? So here, guys, there's 2 parts here. One with no restriction and one with restriction. So solution. No, 10 digits make all the numbers, and the digits are 0 through 9, right? So there's 10. So part 1, there's no restrictions, right? So this is my zip code. There's my first number goes there, or my first digit goes there, second, third, fourth, and fifth. That's why the 5-digit zip code is right here. See, there's my 5-digit zip code. So for part 1, right, there's no restrictions. So how many digits can go here? Any one, because here there's no restrictions, so all 10 can go there. And also for the second digit, third digit, fourth, and fifth. You multiply them out, and that's the answer is 100,000 possible ways. Okay. Now for part 2, it says the first digit cannot be a 0 right here. How many would be possible if the first digit could not be a 0? So then again, right? So this is going to be 9. Why? Because 0 cannot be here, right? So if 0 cannot be here, right? 0 cannot go there, but 1 through 9 can go here. That's why 1, 2, 3, 4, 5, 6, 7, 8, 9 can go here. And then for the rest, there's no restrictions. So 10, 10, 10, and 10. You multiply them out, and you get 90,000. So there's 90,000 possible ways. Okay. This is number 30 from page 477. For many years, the state of California used 3 letters followed by 3 digits on its automobile license plates. Solution. Note, 26 letters are in the alphabet and 10 digits make all the numbers. Why do I put that there? Because at times, guys, I know we all know, right? That people from the U.S. that there's 26 letters, but and also 10 digits. But people from other countries that take courses here in America, maybe their alphabets are more than that. Because I think Mexico, I think there's more letters on their alphabet. Than here, if I'm not mistaken. That's why I put there for students that are actually not from this country. So that way nobody feels left out. Okay. So again, in the American alphabet, there's 26 letters and 10 digits make all the numbers. So for A part, how many different license plates are possible with this arrangement? What arrangement with 3 letters followed by 3 digits? So there are my letters, right? 3 letters followed by 3 digits. So how many letters can go there? 26, 26, 26, and 10, 10, and 10. You multiply it out. So that's your answer. What is it? 17,576,000 possible arrangements. Okay? Now let's try B, another one. When the state ran out of new numbers, the order was reversed to 3 digits followed by 3 letters. How many new license plate numbers were then possible? So again, by now, right, they were reversed. These become your digits, and the last 3 become your letters, right? In multiplication, guys, it doesn't matter, right? I mean, the order, you still get the same thing. But here is going to be 10, 10 and 10, and 26, 26, and 26. And the outcome is the same. Okay. Now for part C. Several years ago, the number described in part B, right, which is this one here, were also used up. So all these numbers were used up. The state then issued plates with 1 letter followed by 3 digits and then 3 letters. How many new license plate numbers will this arrangement provide? So, right, so the first one is going to be a letter, right, because they added a letter at the beginning. And then 3 digits followed by 3 letters. So again, there's no restriction, so that's going to be 26. That's going to be 10, 10, and 10. And 26, 26, 26. And just put it in the calculator. And that's your result. What is it? 456,976,000. Okay, now guys, this is like in real life. For example, when cars were barely made, right? Because there's no license plates in every state that are the same. There's always different license plates. So the more cars that they make, right, the more different license plates they have to get. So the more people that buy cars, right, the more cars that they make, the more new numbers they have to make. So just by adding another digit or another letter, increases the number tremendously. You see, for example, from here, from part B to part C, look how much more it went by adding only 26 letters. Adding like another space for 26 letters. It increased by over 400,000. See? So that's how they do it in real life. Now, this is called n factorial. For any natural number n factorial is n, and then you subtract 1 from n and so forth until you get to 1. And by definition, 0 factorial is equal to 1. Okay, so checkpoint. Let's evaluate 4 factorial. By applying the ruler, it means 4 times 3 times 2 times 1. And then we multiply them, so we get 24. B, 6 factorial, right? So it's going to be 6 times 5 times 4 times 3 times 2 times 1, and then we multiply them, and that's our answer. There's a way to put this in the calculator, okay? But I'm not going to show you how to do that right now. If we have time, I might, or maybe the tutors can actually show you how to do that, or help you how to put that in the calculator. So 1 factorial would just be 1, okay? Now how about D? 6 factorial over 4 factorial. So 6 factorial is going to be 6 times 5 times 4 times 3 times 2 times 1, and 4 factorial will be 4 times 3 times 2 times 1. So the ones, right, so that's equal to 1, that's equal to 1, that's equal to 1, or they cancel, and that's equal to 1. So what's left? 6 times 5 times 1, which is 30. That's the answer for D. Now, permutations. A permutation of a set of elements is an ordering of the elements. For instance, there's 6 permutations, orderings of the letters A, B, and C, right? A, B, and C can be arranged in 6 different orders, right? Because these, even though they're the same letters, right? For permutation, the order matters, or the arrangement matters. Here, okay, this is the key thing here. The order matters. For example, A, B, C, and C, B, A are 2 different orders. Example 3. How many batting orders are possible for a 9-person baseball team? In baseball, guys, there's 9 positions. I mean 9 starters, right? 1 for each position, and they all have to bat. So there are 9 possible choices for the first batter, right? 8 possible choices for the second batter, and so forth. So it's going to be factorial. 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1, which is 362,880. Or, right, or it can be the number of permutations of an element set is n factorial, or it can be 9 factorial, which would be the same thing. Because 9 factorial means 9 times 8 times 7, and so forth. Okay. So that's crucial to know about factorial. Now here's for permutation, here's the formula. If NPR, where R is less than or equal to N, is the number of permutations of N elements taking R at a time. So for example, the N stands for how many total elements are there. And then for R means that you want to arrange them in R ways, or R at a time. Example. I'd like to show this example to show you the difference between permutation and combination, which I'm going to do here. I'm going to do it right here. Say that I have 3 letters, A, B, and C. I would like to know how many 2-letter arrangements are possible. Order, here guys, remember, order matters with permutations. That's the difference between permutation and combinations. So we always want to get some kind of a sequence. For example, A and B, and then BA, right? So these two are 2 different arrangements. Then we have A and C and C and A. And then B and C and C and B. So there's going to be 6 possible arrangements. Okay, I like to show this with 3 letters because the more that you use, the more they're going to be, right? And it's hard to see them because we might get confused with the ordering. That's why you use a formula here. Here, guys, the N, right? The N is going to be 3, right? Because there's 3 letters and you want to put them in 2s, arrangements of 2s. So it'll be 3P2. And again, you can plug it down in the calculator, but I'm going to show you how to do it by hand. So this is 3 factorial. 3 minus 2 is 1 factorial, right? So we expand it. So it'll be 3 times 2 times 1. The answer is 6, right? Then we get 6. Or there's another way to do it. You have 3 letters and 1 arrangement of 2, right? So you have 2, so you're gonna, you want 2 letters, so there's 1, 2. How many can go here out of 3 letters, right? All 3 can go here, right? On the first blank. Say that you after you after you got the A, B, and C, right? Say that you want A to be there, and then there's 2 left to choose from, right? So this is an alternative to the permutation formula, which is equal to 6. Number 40 from page 478. From a cooler with 8 cans of different kinds of soda, 3 are selected for 3 people. How many ways can this be done? So again, permutation wise is going to be 8, right? You have 8 total, and you want to put them in sets of 3s. There's going to be 8 permutation 3. Right? Why did I stop here at 5 factorial? Because I know these are going to cancel. So just multiply 8 times 7 times 6, and it gives you 336. Okay, now what's the other? The alternative, right? There's 8, but you have 8 cans, and you want to arrange them in 3. So you're going to put 3 blanks are right because you want them in 3s and sets of 3s. So how many can go here? Say you have 8 different sodas, right? So if you choose one soda here, right, it can now repeat. That's why it's 8, and then you got 7, and then you got 6. You multiply them out, and that's your answer. For the permutation, it has 2 ways to do. To get the answer. But for the combinations, it doesn't. It only has 1 way, which that's next. Here, the order does not matter. So, for example, AB is the same thing as BA, right? Because the order does not matter. So let's see here. If I have 3 letters, does anybody have a question? You guys okay?
Sorry, Mr. Rizaldi, I didn't get the last part of the last example. Do you mind if you could
Let me go back.
speak to me again?
Let me go back. You mean here?
Yeah, why is it 8 times 7 times 6?
Because say you have 8 different types of sodas, right? 8 different types of sodas. You got Pepsi, you got Coke, you got Diet Coke, and so forth. And then, right, after you give 1 soda to a person, right, if there was 8, right, how many are left? Wouldn't there be 7?
Yeah, okay.
And then after you give another soda to another person, right, wouldn't there be 6 left?
Okay, so we only put 3 because it says 3 are selected for 3 people, right? Okay.
Yes. So the first person can choose from 8, and then after the first person chooses, there's 7 left, and then 6 left.
So if it said, for example, 4, then we would have to add the 5. Like
8 times,
8,
yes,
7,
yes,
6,
8
5.
times 7 times 6 times 5. Yes.
Okay, thank you.
You okay then?
Yeah, thank you.
Okay, you're welcome. Okay, now guys, here comes the combination then, okay? Again, going back to the three letters, right? A, B, and C. So AB, guys, is not the same thing as, AB and BA are the same thing. So it's AB, AC, and BC. So the answer is 3. Because here, the order does not matter. For example, on the permutations, AB was one specific way, and then BA was another one. Here, guys, AB and BA is the same thing. That's why order does not matter. So, but if we plug into the formula, it's going to be 3 combination 2, right? And we have to follow the formula here. Which would be 3 factorial times 2 factorial times 1 factorial, which would be 3 times 2 times 1, and this will be 2 times 1 times 1. So we're left with 3 over 1, which is equal to 3. Now, example, this is from page 46. Number 46 from page 478. It says 4 items are to be randomly selected from a list of 25 items on an assembly line in order to determine the defect rate. How many different samples of 4 items can be chosen? Okay. So it's going to be combination, right? Because here, the order does not matter. Right, so we got 25 and 4, so it's going to be 25 combination 4. And again, you can plug that in just like that in the calculator, guys, to get the answer. Maybe the tutors can show you or can help you how to do that, if you guys don't know. So here we have 25 factorial over 4 factorial, and 25 minus 4 is 21. Right, so I stop here at 21 factorial because they're going to cancel there. Those cancel, right, so it's equal to 1. And now here, what's 4 times 3 times 2? Won't it be 24? 4 times 3 is 12, times 2 is 24. So those cancel with the 24 there. So what's left? 25 times 23 times 22, which is equal to 12,650. Okay. Now, hey guys, here are the key things, guys, okay? I put this here at the end so you guys can know like the difference. There's always like clues, because at times students get confused with they don't know what to use, and they begin guessing and they guess wrong. There's always like some key words that will tell you which one it is. Okay, for example, for permutations, here are the clue words: arrangement, schedule, order, or order matters. And for combination, these are my clue words: group, committee, set, sample, order does not matter. Example: this is number 59 from page 478. A lottery game requires that you pick 6 different numbers. I forgot to put your numbers, guys. Lottery game requires that you pick 6 different numbers from 1 to 99. If you pick all 6 winning numbers, you win $4 million. Okay, here's A part. How many ways are there to choose 6 numbers if order is not important? So here, guys, we're going to use combination, right? Because order is not important. So it's going to be 99 combination 6, because there's 99 numbers to choose from, and they want them in sets of 6, right? So there's my formula, and then this is my result. What is it, like 1,120,529,256? Now for part B, order matters. So this is going to be permutation. So again, same formula, but this is going to be a lot more. So that's your answer right there, guys. 806 billion, and you can read it from there. Okay? 806 billion, 781 million, 64,320. Now, this is number 60 from page 479. This is a little bit more challenging, guys, okay? Because I have to give you something a little bit more challenging, but I already set up the foundation. And exercise 59. If you pick 5 out of 6 numbers correctly, you'll win $5,000. Okay? And how many ways can you pick exactly 5 of the 6 winning numbers without regard to order? So this is going to be a combination, right? Okay, now. But this is a little bit more challenging, okay? Check this out. Because if you don't win, right, the grand prize, right, the lotto, but if you get 5 out of 6 right, you win something, you win 5,000. So then, right, so 5 out of 6, so here it is. So to win the 5,000, you have to get 5 out of the 6 winning numbers. So it's going to be 6 combination 5. Remember, the lottery requires need to pick 6 numbers from the 99. So here, guys, we're missing one number, right? So then here, we win a 1 out of 93 losing numbers because you don't win the lotto, but you win the $5,000 by getting 5 right. So then this is going to be 93 combination 1. Okay, now check this out. Right, this equal to 99 if you add them, and this is going to equal to 6. I mean, these must equal to 99 also, the first numbers. That's how you can tell how to set it up. And then this will be the 6. The 5 and the 1 will be 6. Okay, and again, this is you know how to set these type of problems up. So we multiply them, right? So this is equal to 6, and that will be 93. We multiply them out. So the answer is 558. Okay. Now, I believe this is the last one because it's already 4 o'clock. But anyway, this is the last one. Why did I do this is 60, this is 58? Because it seems, guys, on the odd problems, they're very simple. On the even ones are harder. And most instructors, they like to give the even numbers as homework because the odd ones you can check the answer in the back of the book. But it seems that the even numbers are harder. That's why this one, that's why I have to do, if I did 59, then I did 60, then 58 is something like number 60, okay? But check this out. It says, a financial advisor offers 8 mutual funds in the high risk category, 7 in the moderate risk category, and 10 in the low risk category. An investor decides to invest 3 high risk funds, 4 moderate risk funds, and 3 low risk funds. How many ways can the investor do this? Okay, so let's do this. Solution. If you read the problem carefully, order does not matter. Because if you have 8, right, if you have 8 mutual funds at risk, it doesn't matter which ones they are, right? Like, for example, if one's higher than the other one, right? It doesn't because they're all high risk. So here the order does not matter. So we're going to put from the 8, high risk, I'm going to choose 3. Invest 3 from the 8, which is going to be 8 combination 3. Now, right from the 7, moderate risk, I'm going to choose 4. Invest 4 from the 7, and moderate risk is going to be 7 combination 4. And then finally, from the 10 and no risk, I want to invest with 3. So invest 3 from the 10 and no risk. So then you're going to get the answer for each one of these, and then you're going to multiply them out. So for example, 8 combination 3 is equal to 56. 7 combination 4 is equal to 35. And 10 combination 3 is equal to 120. We multiply them out. So that's my result. So it's going to be, the investor has 235,200 ways to select the funds. And I believe that's my PowerPoint. Okay, again, guys, if you ever want the PowerPoints that you can actually have the animation with, send me an email and I'll send you everything that I have. Okay? Because the ones that are recorded, you cannot do the animation, but you can pause it and rewind and stuff like that. Okay? Send me an email and I can send them to you. Thank you, guys. Let me stop sharing my screen here.
Thank you very much.
We're going to go ahead and take this time to thank Mr. Isasi for this presentation. Thank you guys for all the audience for being with us today. Also to let you guys know, there are tutors right now available. If you need any help, you can always raise your hand or let us know through the chat, and afterwards we can go ahead and help you. Also, just to let you know, next week's on May 7th, we're gonna have our final exam review both on the Math 1314 room and on this room, the Math 1324. So you're always welcome to come join us for a final exam review. But other than that, if you don't have any questions, you're free to go. This concludes our session for today. You have a good weekend. Stay safe. And for those who need help or want to talk to a tutor afterwards, just go ahead and let us know either through the chat or by raising your hand. But once again, thank you so much, Mr. Isasi, for presenting to us today.
You're welcome. You're welcome very much.